In the previous lesson, we introduced the concept of algorithms. In this lesson, we'll go a little bit deeper to find out what algorithms really are, how they're formatted, and how they're written. The definition of an algorithm is a process or set of rules to be followed in calculations or other problem-solving operations. So remember, in the programming process, in the iterative development process, the formation of an algorithm came after having finalized an idea. So as you discovered, these are the 4 reasons why algorithms are important, and we'll discuss these just a little bit. Number 1, they are tools for problem solving. They are the tools for computational problem solving. You wouldn't expect a tree to turn into a cabinet without having some tools, and likewise, you can't expect an idea to turn into a program without algorithms. Secondly, they help us find an efficient step-by-step process for working out a solution. A lot of times before we have really thought through the algorithm, we kind of think we know how the algorithm is going to work, and when we really set to thinking about it, we realize that there is another way that is going to be better. Number 3, they provide an outline for how to write the code for a specific program. Probably when you've been asked to write essays by your teachers, they've taught you or expected you to create an outline prior to actually starting the writing process, along the same lines as this algorithm, that you would want to have your algorithm well thought out and complete before you start writing code. And finally, algorithms help us construct and express a detailed sequence of operations that harness the power of our computers. Just about any algorithm that you are going to develop, the goal of that is to utilize the computer to its full potential in your program. So the goal of this course is to help you develop into an algorithmic thinker, or you might use the term a computational thinker. Algorithmic thinking or computational thinking is the process that is behind organizing complex thoughts into some sort of logical and structured order and constructing a conceptual solution that can later be implemented. And the skills that we need would be analysis, how to look at a problem, analyze exactly what needs to be done to solve it, to identify a problem in the first place, to recognize which tools we have to work with, and then finally to design an effective and an efficient solution. So most algorithms, even though some may look very complex and scary, can be broken down into some familiar patterns. And these are the patterns that control the flow of execution for the instructions, for the steps in our programs. And these patterns ensure that all of the right steps are performed in the right way and in the right order. And there are 3 main patterns that you will find. You will find sequencing, selection, and iteration. To introduce sequencing briefly, because we are going to go into much more detail later, sequencing means that actions are performed in order, one after another. And oftentimes this is referred to as a linear algorithm because everything is in line in the correct order and it's executed one thing after another. And these are just some examples of what sequencing might look like. On the left, you see an example from Scratch. You will actually work with this particular algorithm. And then on the right, you see an example from the APCSP exam, a type of thing that you might see on there, a robot algorithm. And this algorithm will move the robot to its desired destination. Selection uses an if-then type of logic to tell the computer how to select which step to follow or which step to take or which sequence should be executed. And so the example you can see on the left with Scratch would be that after being asked a question of if you're thirsty, you would say, well, if the answer is yes, then finally ask what you would like to drink. If the answer is not yes, then there's no use in asking what you'd like to drink. On the right, you can see that the robot has some selection that it can make. So it can check and see if it's possible to move right, then it will. If it's not, then it can't. And the last structure is iteration, and this uses repetition. So actions are repeated over and over until a condition is met. And you can see on the left, this is an example from Scratch, the steps in blue are repeated 4 times, iterated through 4 times, or until the number 4 is reached. And on the right, in the robot example, you can see that iteration is used here because it is going to have one particular pattern to follow, but repeating it 2 times will cause the robot to reach the desired destination. If those went right over your head, don't worry, because we are going to go into those in a lot more detail in later lessons. Writing the best algorithms. On screen, you see well-written algorithms are specific and precise. It is definitely important that the algorithm be communicated in some form that ensures that the individual steps of the algorithm are perfectly understood and executed exactly the way they were intended. We will definitely spend some more time on how to make your algorithms specific and precise. Here's an example of an algorithm you have probably used more than once in your life, and it's the algorithm for getting dressed. Both of the algorithms that you see, one on the left, two on the right, contain very much the same information, but the second version is more specific and precise. It is more clearly expressed as a sequence of instructions compared to the first version. So let's look at a few of the features that the second version has that make it more useful as an algorithm than the first. So what's important when looking at algorithms? The format is important. It's important that each instruction be written clearly on its own line. And we can see that algorithm 1 was all written on one line, whereas algorithm 2 was split up into 4 individual lines. And it just makes it easier to read, and we're sure which one comes first. Secondly, algorithms are going to feature imperative statements. Imperative statements, if you've taken a foreign language, you might have encountered imperatives before. Each instruction uses a command, and that command should clearly note which operation should be performed. So when we go back and look at algorithm 1, we can see that there are no imperative statements here. There are no commands. There are simply a list of clothing items without the commands telling what to do with them. Whereas in algorithm 2, we include put on to explain further what needs to be done with those items. And last but not least, an algorithm is going to have descriptive qualifiers. So each instruction should include distinctions when they are necessary. So as an example, if we go back, we can see that in the middle of algorithm 1, there are 2 shoes, but it doesn't tell which shoe is which. So in other words, the person or the computer trying to follow these constructions doesn't know which shoe is being referred to by this second area. And in algorithm 2, it states clearly left shoe and right shoe. And again, those are the descriptive qualifiers, and they're not necessary for the pants or the shirt, but they are for the shoes. All right, so what information should algorithms include? First, let's talk about what shouldn't be there. And instructions must be executed exactly as intended. So if a person or a computer, either way, reads an algorithm, they need to understand it with 100% certainty. And so again, at the previous slide, those 3 things, the format, the imperative statements, the descriptive qualifiers, all of those are very important information to include. So let's take a look at another basic algorithm. This one is a little more complicated than just getting dressed. This is the algorithm for averaging a list of numbers. Notice it is not stated how many numbers are in the list, just that there is a list of them. And so the first step would be to find the sum of all the numbers, add the numbers up in the list. And the second step would be to take that quantity and divide it by the number of items in the list. And that will work every single time. It is clearly stated, and everyone would know how to follow it. All right, so examples of other algorithms that you may have encountered. A recipe could be considered to be an algorithm. It tells the format of the instructions, whether you're supposed to boil or fry or bake something. It gives all the descriptive qualifiers that would be needed, the quantities that would be needed, in addition to all the ingredients. Sorting out laundry. So depending on your washer and your detergent and all of those things, you may have your own method of sorting laundry that works, but you may have some special situations. For example, if you get a new red sweater, then you might have to come up with a new algorithm for sorting your laundry. Putting things in alphabetical order. If you were given a stack of papers that was all mixed up and told, I need you to put this in alphabetical order, instead of just starting with the first one and hoping that the next one was later in the alphabet, you would probably come up with a plan such as creating stacks for each letter, or maybe looking at the first and the second and comparing them and deciding, which should go on which stack. So there are all kinds of things that would be involved in that, but probably you would come up with a very specific plan that would end up with that stack of papers being alphabetized. And of course, a Rubik's Cube, if you've ever worked with one of those, there are many, many different algorithms for solving a side or the entire cube based on, what color's in the middle or what colors are in the corner. And they're just really a very clear set of steps that somebody will come up with that will allow them to solve part or all of the Rubik's Cube every time. So far, we have done basic examples for how algorithms are structured in text, in Scratch, and for the robot problems on the AP. There are different formats that an algorithm can take, and we will go further into some of these later on in the course. But some examples are flowcharts, pseudocode, mathematical notation, an actual programming language. Each of these formats dictates its own specific style, syntax that is designed to ensure that any algorithm can be expressed in an understandable and clearly unambiguous way.